Today's topic is on grease lubrication mechanism in rolling bearings. Before going to the topic, I would like to introduce myself. I'm Sathwik Chatra, part of the SKF Research and Technology Development, Houten, the Netherlands. Before going to the topic as it is, I wanted to say a few words about the topic. First of all, what we're going to talk today is on the generalized mechanism, lubrication mechanism in the rolling bearings, where your rolling bearings is equipped with the grease as a lubricant. And moreover, we will be concentrating more on the film thickness aspects of the grease lubrication in the rolling bearings. The reason to do so is that we believe that formation of a healthy film thickness and deterioration of the film thickness is having a direct impact on the bearing performance. That means when you have a very good developed film thickness, you're going to get a very good grease performance and thus the good bearing performance too. The entire summary or entire part of the presentation is kind of a summary of the last 2 to 3 decades of R&D work done in the SKF pertaining to the grease lubrication aspects. But I have also included a few parts from the literature or the information available in the public domain, mainly from the academicians. So the reason to do so is to have an entirety or the completeness for the topic itself. So this is the graphical abstract, what I'm going to talk today. So here there will be 2 different phases in the lubrication mechanism, and in each phase there will be different aspects will take place, and we will discuss on these aspects, what is the impact of these aspects and how the changes of these aspects will have an impact on the grease lubrication performances in a rolling bearing application. An introduction. So before going to the such topic, let me introduce a bit about the grease itself. If you look back into our elementary school, probably you would have learned a topic called as colloidal molecules. So when you want to call something as a colloid, normally it should have 2 different components. One is a dispersion phase and another is the dispersion medium. Grease is a colloidal molecules. That means it has 2 components in it. One is the thickening agent, which acts as the dispersion phase. Another one is the liquid lubricant, which acts as the dispersion medium. So if I want to define a grease, it's a solid to semi-solid product or a dispersion of a thickening agent in a liquid lubricant. So then how exactly this base oil is kept inside the thickener structure? It's mainly by the combination of the van der Waals forces and capillary forces. In the same way, thickener molecules are also can interact between themselves, mainly by the hydrogen bonding, ionic bonding, or even by the van der Waals forces. If you take an example of a lithium grease, so then the thickener fiber length may vary from 1 to 100 microns. So what you see here is a 2-dimensional image of a lithium grease. It's a simple lithium grease with the mineral oil. So this image is taken by using an instrument called atomic force microscopy, AFM. So here what you see is a helical coiled structure. Those are the thickener fibers, and you could clearly see that they interact with each other and they crisscross to form a microstructure. And in between the microstructure, you have an empty space where the base oil, the liquid lubricant will be present. So in this case, it looks like an yellowish or the brownish color. Grease components, as I already told, there are 2 different grease components. One is thickening agent. So thickening agent can be soap-based. That means it can be lithium, sodium, or calcium. So you can add a cross-linking agent to it to make it into a complex grease. But there are also non-soap-based thickening agents like polyurea, clay, or polymer-based like PTFE or SKF proprietary polyethylene greases. And when you think from the base oils, so base oils can be mineral oil, synthetics, or even natural esters. As a third component, grease also has certain components called as additives, which are mainly used for the performance enhancement. For example, if your application has a higher load situation, then your grease composition should hold certain percentage of the extreme pressure additives. In the same way, you have an application wherein water ingress will be there, a higher percentage of humidity will be there, then your grease composition should hold a good percentage of the anti-corrosion. In the same way, for high temperature application, you should have a better level of antioxidant concentration in it. As a function, normally I already said that, okay, grease also contains oil. So then there should be some reasons why we should lubricate with the greases than just lubricating with the oil. Definitely grease has better advantages, at least in few things. For example, one is inherent sealing. Grease provides an inherent sealing such that it can avoid the entry of the contaminations like dirt particles or water into the contacts. And second is the under normal operation condition, grease never leaks. The reason to do is they have a structure. So grease does not move until unless you prompt it to do so. If I take an analogy of it, so I simply take a sponge dipped in the water. So such that if you take out the sponge from the water, then until unless you press the sponge, water is not going to ooze out. Grease also functions in the same way. So here you need to apply certain forces, like maybe the shear forces, what happens normally in a bearing application. And another important aspect is the good lubricity. That means low friction. So what happens here is that when you are lubricate a bearing with a grease, so normally in the contact, only the minimum quantity of the lubricant is available. So when compared to an oil lubrication where you have a bulk quantity, so because of that, you are going to get a lower friction compared to an oil lubricated bearing. So does operating condition influence on the grease lubrication processes? Yes. So grease lubrication process normally quite different for different conditions and also for the bearing types. That means the general mechanism still holds true, but the different aspects what is happening within that general mechanism, so the rate of those aspects can change or may vary based on the type of the conditions you use and also type of the bearings you use. For example, from the condition point of view, if your application is at a lower speed, so then you can completely neglect the impact of the grease churning losses. And if you are having a higher speed application, then you have a large centrifugal forces that can push the grease from the contact towards the side. So such that in a short period of time, you can enter into a severe starvation situation. In the same way, at higher temperature, it's the oxidation or the loss of the consistency play a major role in defining the grease performances. So when I say lubrication mechanism, it is mainly corresponding to the bearing running under a constant condition with a medium speed. So what is medium speed here? Normally in bearing industry, we nominate the speed with the NDMs. So then medium speed here varies from 100,000 to around 500,000 NDM. And if you want to segregate the grease lubrication mechanism in a bearing running under constant condition, we can roughly do it with the two phases. So one is the churning phase, and another one is the bleeding phase. So before going in detail with these phases, I would like to explain another important aspect called the grease filling. So normally, as a rule of thumb, approximately we recommend a 30% of the free volume to be filled in a bearing with the grease. Mainly, this is for the sealed and shielded bearing. So this quantity is mainly to provide the fully flooded condition, at least during the running in period. So this recommendation of 30% may vary a bit based on your speed condition. For example, if you're using a very high speed and the ultra high speed situation, then this recommendation will be reduced to around 20 to 25%. So what you see now is a very general schematic representation of the grease lubrication mechanism. So here you see the two phases, the churning phase, the bleeding phase, and what will happen after the bleeding phase. So as soon as you fill your bearings and you start the operation of the bearing, that means your bearings start to rotate, immediately grease started to move. part of part of the grease will move towards to the side of the bearing, and this will stay there on the outer part of the bearing, and that particular amount of the grease normally stays there, and they can contribute back to the lubrication process only by the process of the bleeding during the bleeding phase. And another part of the grease which will move towards the cage pockets or the cage bar or even towards the bearing shoulder. There they form the reservoir, and this reservoir formation is mainly dependent on the bearing geometry, cage type, cage material, and also on the rheological properties, the flow properties of the grease. So since in this process, the entire grease itself in the flow, that means there will be a macro flow of the grease towards the contact. So that's why in the contact you have enough quantity of the lubricant. So the film thickness is normally is a fully flooded situation you have. So what now once during the churning phase, more and more greases will start to move away from the contacts and from the swept volume towards to the unswept volume of the bearing. During end of the churning phase, most of the greases will already moved out of the contact zone. Then they will be either placed in the grease reservoirs or even in the shields. So then very less the minimum quantity required for lubrication is left in the contact. So that's where the bleeding phase starts. So normally why we call this as a bleeding phase, because the generalized mechanism accepted in that phase where the lubricant supply happens is mainly due to the oil bleeding from the grease reservoirs. And these grease reservoirs are formed during the churning phase. So here you see the film thickness varying from the starved EHL, mild starvation to the severe starvation. But film thickness itself is a starved EHL, elastohydrodynamic lubrication regime. And there will be replenishment of the lubricant supply into the contacts, maybe by the centrifugal forces and also caused by the grease dynamism. I will tell you what exactly grease dynamism means in the future slides. But there are also some aspects which causes or influences the depletion of the film thickness, like possible oxidation. When this happens, so there will be a possibility of the film breakdown. That means asperity contacts will happen, or metal to contact will happen. So then immediately you are not supplied with the few quantity or the few amount of the lubrication, then this film cannot be recovered back. So that will lead into the bearing failure, and in this case the reason is purely because of the lack of the lubrication. So here, if we look into the temperature profile of these two phases, how exactly it looks. So as I said, when you start bearing operation, grease starts to flow, and it is a complete or entirety of the grease itself is involved in this process. So because of that, the huge viscosity of the grease, then friction torque is going to rise. Because of the friction torque, the temperature profile is also going to rise. So when more and more grease is moved away from the contact towards to the reservoirs and to the shields, so then the viscosity of the total viscosity will be going down, and also the friction torque will reduce such that even temperature profile will reach into a quasi steady state. So, and few greases can do that in a very fast in a short period of time, and few greases will take a long period of time to reach into a quasi steady state of temperature. So that means during bleeding phase you have only constant temperature, stationary temperature. It's also not true, because there will be grease dynamism that also fluctuates a bit of temperature even in the bleeding phase. But if you look into the microstructure aspects of the grease, what happens? So you could clearly see that this is the fresh grease. So once you start operation, you enter into the churning phase, then you enter into the bleeding phase. When you take the AFM image of a bleeding phase, the grease which was there in the bleeding phase, then you clearly see that most of the thickener fibers is completely destroyed. Only you are left with the certain medium-sized fibers, and most of the fibers are degraded into short fragments. So here, what we see a pictorial representation of the grease positioning. That means how exactly reservoirs are formed. So this is the situation before the start. You fill the greases in the available free space free volume. So then you start your operation. So grease started to flow, our macro flow will happen in the beginning. So then after 55 minutes, still there is a flow, grease will migrate to different parts of the bearing. But remarkable thing is that when you compare the picture of 55 minutes with around 532 hours, you could clearly see that. So the grease is, the positioning of grease is not so much changed between these two pictures. So what it indicates, particularly for this example, the churning phase was finished roughly within an hour. So this is the corresponding temperature for that. The grease flow is still going to happen here, so that the friction torque is increasing, then temperature profile is increasing, then grease took its position in the bearing. So then there is no macro flow of the grease, then you witness a quasi steady state of the temperature profile. So another part in the churning phase is the formation of the channel. So how exactly the process of creating and formation of channel happens in this case. So this is again a schematic representation of it. So what you see is a bearing arrangement. You have the rolling element, the inner ring, outer ring, and a chunk of grease. So this situation is just before starting the your bearing operation. When you start bearing operation, the rolling element started to move. So then it has to cut across into the lump of the grease. When it cut across and move forward, what it does behind it, it started to create a space. And when the second element comes, that also does the similar process, such that it will add few more space for the behind this. So this process is continuous until and unless you reach to a situation where a clear channel is created. So that's where the channeling process is finished in the churning process. So when all these things are happening, you have a very high drag force and churning, that as a corresponding temperature will be very high. And when the channeling is formed, or the clearing is formed, so then you don't have any drag forces or very low drag forces, because there is no macro flow of the grease now, and temperature profile will reach back into the quasi steady state. So we have seen that there are possibilities. Some greases will finish the channeling process in a very short period of time, and some greases will take a long period of time. So can we, based on the temperature profile, can we segregate a temperature channeling behavior based on the temperature profile? Yes, it is possible. What we have done here, a few examples like the green markers and the blue markers, they finished the grease channeling process within less than 3 hours, and we consider these type of greases as the good or the peak type of channeling greases. In the same way, few greases like the red one and the orange markers here, they took more than 4 hours, and we consider these greases as the poor or plateau type greases. And mainly poor or plateau type greases, sometimes it will take around 24 hours, and we have seen some of the examples where it also take more than 48 hours to reach into a steady state of temperature profile. So is it channeling is condition dependent? So before going to answer that question, I wanted to tell that there are two things here. One is channeling properties, and another thing is channeling behavior. These two are very different aspects. For example, channeling properties are the grease properties. So for example, if a grease has a channeling property, then it will act as a good channeling grease. If a grease lacks the channeling properties, then it definitely acts as a poor channeling greases. Here in this example, the example what we provided, even though we vary the speed condition from very low to very high speed, still a good channeling grease behaved as a good channeling grease itself. In the same way, a poor channeling grease behaved as poor channeling grease itself in the variable speed conditions. So, but the thing is that in this example we could not able to show, but if you the situation comes that the grease is exceeding its limiting condition factors, so then there is a possibility that a good channeling grease can fail to act as a good channeling grease itself. So we have seen that, okay, there are two different channeling behavior, channeling types based on the channeling behavior. Then does this has an impact on the grease performance or the grease properties? To do so, what we have done is that we used an instrument called rheometer. This is mainly used to study the rheological properties of the greases. And here we study the yield stress. So what is an yield stress? Yield stress is the minimum force required for the grease to flow or the move. So what we have done is, in the beginning, we measure the yield stress for the fresh greases. And later, again, after finishing our churning experiment, we again measure the yield stress. So what you see is a good channeling grease, like the green and blue markers, even at the end of the channeling process, so they still hold a similar kind of the yield stress. So yield stress represents again the mechanical stability of the grease. So on the other hand, a poor channeling greases clearly showed a drastic decrease in the yield stress after the channeling period. So if I quantify these amounts in into an quantified amount, then I could clearly see that good channeling greases, the change was around 10%, while the change in the poor channeling grease was more than 60%. So that means the grease is severely aged here. This definitely has an impact on the grease properties, like the maybe the viscosity itself, and also the bleeding properties, and rest of the grease properties also can have an impact because of the severe aging. So what you see here is a schematic representation of the grease microstructure and how this channeling behavior has an impact on the grease microstructure. So here what you see is a fresh grease of the poor channeling grease and also the good channeling grease. So in both the cases, fresh greases has long fibers, they are interconnected, they created a beautiful microstructure. So immediately after channeling itself, you could see that in case of the poor channeling greases, it's completely destroyed. Long fibers are broken down into short fragments and very less of the medium fragments. But in the case of good channeling grease, you clearly see that after channeling, still there is a huge amount of the long fibers that's left. And okay, there are few amounts of the medium-sized fibers and also short fragments were formed, but still you had a good proportion of the uh, long fibers. And this is the reason why in the yield stress measurement, why you saw that a good channeling grease had still maintained its yield stress even after the finishing of the channeling process. Here, what do you see is the formation of the reservoir. So I already explained that once you start your operation, the grease which is present between the rollers and outer ring will be pressed towards to the outer ring or into the shields, and that will stay there, and they will contribute back to the lubrication by the oil bleeding from the reservoirs they formed. On the other hand, the grease which is present on the inner ring and the rollers, they can part of the grease will be pressed into the cage bars, and they will form or attach into the cage bars. They will form reservoirs. The quantity of the grease can attach is heavily depend upon the bearing geometry of the cage type, and also on the flow properties of the rheological properties of the grease itself. And here you see that how exactly the grease viscosity is going to change when you apply a different shear rate. In bearing contacts, the shear rate may vary from around 10 to the power 7 to 10 to the power 4 per second. This is again a schematic representation of a DGBB, and this is after the finishing of the channeling or the churning process. Here you clearly see that the grease reservoirs are formed on the shields and the cage bars. And here we will show a movie, a small video of how exactly grease mixing and flow of the grease is happening. And here we used a CRB, and the grease used is a lithium complex grease. So here you see that when we increase the speed of the operation, how exactly grease started to flow, or migration of the grease, how exactly it happens, and how the redistribution of the grease is going to take place in the bearing. We're slowly increasing the speed now. You could see the grease has a tendency to move now. Yeah, you could clearly see that in the picture. So grease is started to flow in this part. Yeah, so now it's in the top speed. You could see most of the grease is already redistributed in the bearing, and according to that, even temperature is also increasing. So here, what you see is the film thickness in the initial condition. So this work is done by Kanata et al. So what they have done is they used three different polyurea greases designated as grease A, B, and C, and they also used three different base oil properties, like they changed the base of viscosity, one with the 100 centistokes and another one with the 30 centistokes, another one with the 50 centistokes at the 40 degrees centigrade. So that designated as 1, 2, 3. And what is the unique about, first of all, this is a ball in it's a single contact experiment as a ball on disc experiment, and these are the interferometry images what you see, and this image is taken at the end of the running. And the uniqueness about this image is that so every picture is different. So what it indicates that the film thickness, at least in the initial condition, is very unique based on the composition of the grease. The reason is that entirety, that means grease itself is involved in the formation of the film thickness. You also can see the deposition of the thickener in the contacts during this period. So at the end, films are really thicker than predicted with the base oil viscosity itself. So now we move into the bleeding phase. So here you could see that this is a schematic representation of the roll or raceway contact separated by a lubricant film. So here there are two aspects here. First, okay, this is what you see is the layer thickness, which is completely different from the film thickness. So what will happen? The film thickness has to maintain here. That there should, as I said in the beginning, if you have a good film thickness for a long period of time, so then you will be in a good grease performance, and that's the good bearing performance. So to maintain a healthy film thickness, there are different aspects will happen here. So few aspects will contribute to the formation of the film thickness, and few aspects will be resulting in the depletion of the film thickness. So for example, so in this particular phase, oil has to bleed from the grease reservoir, and this bleeding mainly happen due to the shear and also due to the capillary forces. If your grease is stored in the shields or the bearing shoulder, then main mechanism of oil bleeding is through the capillary forces, or also by the Marangoni effects, where the temperature gradients will have a tendency for the flow of the grease. Then there is also another possibility. The flow also can be induced by the centrifugal forces. So in this case, the centrifugal force induces the flow towards to the contact. So these will contribute into the formation of the film thickness. In the same way, there are other aspects like pressure, for example, pressure induced side flow. So in this case, what will happen is that because of the severe contact pressure, lubricant will have a tendency to move away from the contact to the sides of the bearing. In the same way, centrifugal force also can play a role here. Instead of moving towards the contact, these forces can also move the lubricant towards to the side of the bearing. And if you have a more percentage of smaller molecular weight molecules, then evaporation can cause, and there is also possibility of the cage scrapping. Normally, during the cage scrapping, grease normally thrown towards the sides of the bearing, and these aspects will contribute into the depletion of the film thickness. And another possibility is oxidation. When oxidation happens in the beginning, it creates a lot of low molecular weights molecules that can evaporate, and also in the later stage of oxidation, it produces the varnish or the sludge, so that never contribute to the lubrication purpose. So here again, this will be reason for the depletion. But there is also a replenishment caused by the grease dynamics. So grease dynamics, in the sense, a lump of grease can fall back into the contacts and contributes into the formation of the film thickness itself. Then at that point of time, you have a very small period of the micro channeling, and the temperature can rise back even in the bleeding phase. So this is again a schematic representation where I'm showing the balance. So if you want to have an healthy EHL on your track, so then you should maintain a oil volume. So that can be balanced by the feed and loss mechanism. So that means the grease can contribute to the lubricant, to the contact, to supply the lubricant, one by the capillary forces where the grease is presenting on the shields that can induce the flow of the oil into the contacts. In the same way, the grease which is present in the cage bars can also bleed the oil into the contacts. So these will act as a feeding mechanism. And on the same way, oil molecules or the oil layers can move towards the side of the bearing due to the contact pressure. So like this, so that will be responsible for the loss of the lubricant. So such that if you wanted to maintain a healthy film for a longer period, you really should have a balance between the feed and loss mechanism. So this is a graph which represents the film thickness over a period of time. So we already discussed that in the early period, you have a very high film thickness compared to the film thickness of the base oil. The reason behind is that you are having a complete grease involved in the formation of the film. In the later stage, the only minimum quantity of the grease is left, mainly during the bleeding phase. So then the film thickness will be reduced, or when compared to the calculated film thickness from the base oil. So this film thickness is very, very less. So this is what is kind of a summary what we have discussed till now. So first of all, okay, grease already distributed in the initial filling, but when you start your bearing operation, grease migration or flow will happen that will redistribute grease in the bearing, and this entire process we call it the churning or the phase 1, and the phase 2 is the bleeding phase, where you need to maintain the balance to have a very healthy film in your contacts. So one of the aspects, the film thickness, a reduction of the film thickness is a starvation. But however, it is not completely clear till today which one happens first. That means whether starvation leads to the reduced film thickness, or the other way around, reduced film thickness leads to the starvation. However, normally from if you calculate the fully flooded film thickness, then when you compare it with the starved situation, the film thickness can reduce up to around 71%. So if the things continue like this, maybe you think that soon we are entering into a dry lubrication, or without any lubricant we will entering into a dry regime. But however, that's not going to happen as easily, because even though side flow happens due to the high contact pressure and also due to the centrifugal forces, but because of the high contact pressure, the oil viscosity is also going to increase in the contact. So that will have a resistance for the flow of the oil molecules from the contacts towards the side, even though you have a high contact pressure and also higher centrifugal forces. And this is also very common in the certain bearing types, like if you're using an SRB, spherical roller bearing, or even an angular contact bearing. So this kind of the movement of the side flow is very common phenomena. So in this slide, what we see is that particularly in this picture on the left hand side, so here you have enough lubricant supply in the contact. So that means the pressure buildup starts relatively far upstream with a near zero pressure gradient. So if you look into this picture where you don't have enough supply of the lubricant in the contacts, so then oil layers from the rollers and the raceway will start to merge and start to create a meniscus, and that is very near to the contact, to the Hudson contacts. So that means pressure distribution has to start from from this point, which is very with a something kind of a non-zero pressure gradient. So what this will do is that this will reduce the film thickness. So if you continue this process, that means the lack of lubricant supply into the contacts continues, then you are entering into a situation of the very low film thickness. So on the other way around, the phase where lubricant supply into the contacts determines the EHL film regime. So that regime we call as a starved lubrication regime, and sometimes this is also called as the parched lubrication. So you could clearly see the characteristic pressure shape of the pressure distribution is completely different in the starved lubrication, and the pressure spikes, which is it comes in the near to the outlet. In the beginning it started to reduce, at the end it easily vanishes. So this is actually normally what happens in the bearing. So this we also can do or simulate this thing in a single contact experiment, where you run a ball on disc experiment with a simple small lubricant volume of the layers of oil, and with an interferometry techniques. So what you see here is the shade represents the film thickness. So in the beginning you have a fully flooded condition. Even with the lower speed, you still have a fully flooded condition. That means you have enough supply of the lubricant into the contacts. So that means the meniscus is not going to come near to the hydrogen contacts, so such that you still have a fully flooded condition. When you increase the speed, so what will happen is that the meniscus will start, and it will reach in or touch into the contact itself. Then the film thickness in the middle will be reduced, and that reduction will also moves further away to the sides of the ridges. So that will result into a mild starvation happen in the beginning. Then you are entering into a severe starved condition. So we can see that in this video how exactly this entire process happens. So this is a ball on disc configuration. What you see, there is a ball and there is a disc, and ball moves on the disc, and there is a lubricant layer which we put. And what we do here is we slowly start to increase the speed of the rotation. So in the beginning, when you are having a lower speed, so you still witness the fully flooded situation, that because oil replenishment happens to the contact quite easily. Rolling is not so faster. When you increase the speed, now we slowly started to increase the speed. So when we increase the speed, so the replenishment is very difficult to happen. The lubricant supply into the contacts will be minimum. So then the meniscus will started to touch into the Hudson contacts. So as a result of that, film thickness started to reduce. And if you continue that process, that means the lubricant supply again and again started to less and less, then you will be entering into a situation called as the starved lubrication, or the severe starved lubrication. So here you see that meniscus has started to approach the contact now, but still you still have a fully flooded condition in this point of time. So when you are entering a starved condition, that means there is a huge possibility of metal to metal contact. So then the film cannot be recovered because you don't have enough lubricant supply in the contacts. So such that the unrecoverable film breakdown will lead or results into the failure of the bearing itself. Now it started to approach to the contact. Yeah, now what you see is a mild starvation in the center. Yes, now it is moved into kind of more starved situation in the center, and that will be start to expand to the sides. So it's a bit quite a long video. This one around 3 minutes, I guess. Yeah. So what do you see now? It's a severely starved situation now. Yeah. So now here what do we see is the replenishment. That means oil has to come back into the contact, right? So in the bearing, its mechanism is still not clearly understood. We still believe that it's a thin layer movement is the reason for it, but we have done some again single contact experiment to see whether the phenomena, what is exact phenomena. So what do we see here is the continuous over rolling of the ball happened. That's why you created a valley and the ridges of the lubricant layers, and this is you consider as a fresh now. And after some time, again we take an image, then we see that some of the lubricant is applied into the contact, and after certain time we see that this the valley is completely filled back with the oil molecules, so the lubricant. So however, this test is like, for example, this is 0th second, and this image is taken around 75 seconds, and this image is taken after around 135 seconds. So but this is not exactly replication of the bearing situation, because in bearing ore rolling happens from the ore rolling happens within fraction of second. So that's why we think that in the bearing the replenishment is mainly happened due to the side flow. So here what we see is the oil bleeding mechanism. So we said that oil bleeding is an important phenomena to maintain a healthy film thickness in a bearing operation. So if you look, this is an AFM pictures. To put it into a model, what we have done, we considered the thickener particles into a rod shaped thing, and to make it into further simplification, we have arranged it octagonally. So here what we try to simulate is grease as a porous medium with a collapsing structure. That means the oil molecules which is present here, after the bleeding, the structure will collapse into like this, such that the future bleeding will be reduced. This is what model says. So when you compare the results from the model to the experimental results, which is in the models in the dotted lines or the straight line, then experimental measures in the points. So you could clearly see that in the beginning, the rate of oil bleeding is quite high. Then after a period of time, rate of oil bleeding become very, very stationary. So this indicates that the collapsing of the structure hinders the oil bleeding. So then important aspect is the grease dynamism. So what we have done here, we used a cylindrical roller bearing and we measure and we run the CRB with a grease with around 6,000 RPM. That means very high speed and around 8.34 kilonewton of the load. So and we always measure the self-induced temperature. So both the pictures are of the same grease. So you could see that in the beginning, the temperature spikes is mainly because of the churning, but after that also you see a lot of temperature spikes were there. So the reason is that over a period of time, the film has started to break. So then metal to metal or asperity contact will be there. So because of that, locally the temperature will rise. This rise in temperature will result in the either more lubricant will bleed from the reservoir or possibility of the grease lump itself falling back into the contacts if it loosely bound into the reservoir. So because of that, you have a micro churning for a short period of time. So then again, the film will heal back. Then after some period, then this again will repeat. This process will repeat. But remarkable thing is that this experiment done in a similar type of bearing and same grease of the same batch is used and same person has run the experiments and same person has filled the grease. However, remarkably, you see that the dynamism is quite different. So this is acceptable thing in a grease lubricated bearing, this chaotic components. So, and we believe that initial conditions are very important. That means the filling. If you vary this filling in the initial condition, and that will have a huge impact on the rate of dynamism, what will happen in the later period of the grease lubricated rolling bearing operation. So in the bleeding phase, aging is also happens. Here, there is a progressive aging of the grease. So there are two different types of aging can happen for the greases. One by the physical aging we call, that means the thickener molecule will start to degrade. So then this will result in the change in the rheology and change in the properties like the bleeding itself. And another possibility is the oxidation that we call as the chemical aging. So there in the beginning you form the low molecular weights and that will form into the varnish or the sludge. So that will not contribute back into the lubrication process such that there will be a loss of lubricity. So if your application in high temperature, then you witness a more of the chemical deterioration. But if your application in a higher speed, so then you witness more of the physical deterioration. Something of between like a medium speed and medium temperature, then both the mechanism of the aging will contribute equally for the deterioration of the grease. So in the chemical aging, particularly in oxidation, so what we see is that concentration of the antioxidant has a huge impact. So in this particular experiment, what they have done is that as soon as the concentration of the antioxidants is lessened or almost nil, so immediately you could see that products of the oxidation, so that we measure to the total acid number here, so that will immediately started to increase. So that's a reaction process. What will happen? Oil will have a reaction with the oxygen molecule. So then in the beginning, you produce the low molecular weight oxidates. Then that will convert into high molecular weight oxidate. Then that will at the end will reach into the formation of the sludge or the varnish deposits. So hence, so this particular step K1 will definitely define the rate of the oxidation. If you have an higher antioxidant concentration, you can really delay this process and you can also delay the onset of the oxidation. So in the same way, the wear particles also has an influence of the rate of oxidation because these wear particles can act as a catalyst for the process of the oxidation. So now we are back in the conclusion. As we said, in grease lubrication, we can have a different phases can be distinguished, like a churning phase and the bleeding phase. In the beginning, mainly in the churning phase, you witness the fully flooded film, and later possibly you have the starved lubrication. In the beginning, it will be mild starvation, and later you will enter into severe starvation. The film thickness may vary due to the dynamic characters of the grease lubrication process, and film thickness is given by the basal viscosity in the bleeding phase mainly, and in the beginning this is given by the grease itself. And grease properties change in time due to the physical and chemical aging of the greases. And life of the grease is limited. If you're using an open bearing, then this limited grease life can be compensated by the process of the relubrication. Before saying thank you to you all, so I wanted to introduce you all to a book. This is Grease Lubrication in Rolling Bearings, published by Willie. This book is written by our senior scientist called Pete M. Lucht. So this book contains almost all the information what is required for the grease lubrication in a rolling bearing. So as I always say, if grease lubrication would have been a religion, and this book should be the holy book of that religion. Thank you all for listening till now. Thank you very much.